All right, so today we are going to start talking about Chapter 8. I'm going to go through 8.1 and 8.2 with you. Chapter 8 involves covalent bonding, so we've been talking about ionic bonding, right? Ionic bonding being when we have a metal and a nonmetal, right? We can say the metal has one valence electron, the nonmetal has 7. In this case, sodium has one valence electron, chlorine has 7. Okay? We know that in this case, sodium gives its one electron to chlorine. By doing so, sodium forms a +1 ion, chlorine forms a -1 ion, right? And those positive and negative ions attract to form the ionic bond. So in this case, one atom will donate or completely give up the electron to the other, right? Well, in covalent bonding, that doesn't happen. It happens by sharing electrons. Okay, so neither side wants to give up any electrons, but instead one shares with the other and vice versa. So what that should tell you right off the bat is in an ionic bond we have between a metal and a nonmetal, where one gives electrons, the other takes electrons. Well, if both sides in a covalent bond don't want to give up any electrons, they want to take electrons, that means that they're between two nonmetals. So that's an important thing to understand, is covalent bonding is between two nonmetals. Okay? So what we're going to look at is a little bit about covalent bonds. All of this is on Google Classroom for you to look at, so I'm just kind of skipping through a little bit to the big points. All right. So again, recall that ionic bonds form when we combine atoms and give up or accept electrons. In covalent bonding, they're shared. Okay, so electrons are shared. The octet rule still holds true. So we're still trying to get to 8 valence electrons for everything, but in order to do that in this case, we're going to share the electrons between atoms. When a covalent bond is formed, we call that a molecule. Okay? So a molecule is when you have 2 or more covalently bonded substances. So for example, O2, it's oxygen. 2 oxygens bonded together form an oxygen molecule. Chlorine is also Cl2. That is also a molecule. All right, H2O, which is water, is also a molecule. Now, if we have a covalently bonded group of atoms, such as oxygen, where they're both the same element, okay, we call that a diatomic molecule. Diatomic, di meaning 2, atomic is atom, so 2 atoms of the same element. So for example, O2 is a diatomic molecule. Cl2 is a diatomic molecule. That's their natural state. That's how you're going to find them in nature. Okay? There's 7 diatomics that we want to worry about. Here's an easy way to remember them. Hibberfunkel.
Oh.
Hibberfunkel, Mr. Luker.
I'm over here to tell you.
Okay? Hydrogen, iodine, bromine, fluorine, oxygen, nitrogen, chlorine. Those 7 are your diatomics. Those are all going to be found in nature, bonded with another of its own kind. So for example, hydrogen is going to be H2. Fluorine, F2. Fluorine, Cl2, so on and so forth. Okay? So those are going to be your diatomics. All right? So as we go, we're going to see how these bonds are going to be made. All right? So those are your diatomic molecules. If you have a molecule comprised of more than one atom, such as water, then we call it a molecular compound. Okay? An ionic compound would be an example of, say, table salt, sodium chloride. A molecular compound would be H2O, 2 parts hydrogen, 1 part oxygen. Okay? And then if we want to represent that, one way we can do that is by writing the molecular formula, which all of these are your molecular formulas. 2 hydrogens, 1 oxygen. It just tells you what is inside of that compound. It doesn't necessarily tell you the structure or what it looks like, how they're arranged, but it tells you what's inside of it. Okay? So that is one way to represent these molecules. What are some other ways that we can look at them? All right? So these all represent ammonia. And ammonia is NH3, if you can see this. Okay? So this would be the molecular formula for ammonia. It tells you that there's 1 nitrogen bonded to 3 hydrogens. Well, it doesn't tell you what the structure is. Okay? if you look at the structural formula, you can see that this one nitrogen has 3 hydrogens bonded to it. Okay? Another way you can look at it is you have to remember that these are 3-dimensional objects, right? They're not just on 2-dimensional paper. So how can we show that there's shape and texture and depth? All right, there's a couple different ways we can do that. This one's called the space-filling molecular model. All right, so the blue sphere in the middle represents nitrogen. The white spheres around it represent the hydrogens. Another one would be the perspective drawing. These triangles, the bigger the triangle gets, that means it's coming closer to you. So think about, you have a central nitrogen. This hydrogen here is coming out towards you. And these 2 hydrogens, the triangle's getting smaller, which means they're going back at angles. It's almost like a tripod. You have 1 sticking out this way and 2 sticking out in the back of the paper. And then you can kind of see it better here. This is a ball and stick model. You're going to see this quite often. Again, here's your nitrogen, hydrogens. The sticks themselves represent the bonds that form between those atoms. Okay? So these are all just different ways that you can represent these molecules, and you're going to be seeing all of them in some extent. Okay? But they give us a good perception of what these things look like. We're going to look more at the structure as we go. Okay, so for example, here's carbon dioxide. Carbon dioxide is called a linear molecule. It has a linear structure. It's called linear because all of those atoms are in a straight line. That's in opposition to water, which is called a bent molecule. Okay, because it's in a bent shape. And all these shapes are basically based on electrons. Okay, they have to do with electrons, and we'll talk about why those electrons give them those shapes. All right. Some of them are a little bit different. All right, here you have 2 carbons bonded to an oxygen with all these little hydrogens attached to them that way. So we'll look more at the shapes and structures later on. Okay? If we do again look at a quick difference between ionic compounds and molecular compounds. Okay? Ionic compound would just be sodium chloride, NaCl, but we know that they can kind of make this lattice type structure. You can take sodium chlorides and just keep alternating them, and you can go really on forever, there's no limit, but they just kind of make this array, this lattice structure of ionic compounds that just keep going, 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 depending on just how big, how much ions you have, okay? Molecular formula, H2O, they're always their own entity, but again, it's just counting how many you have. So in this case, here's water, right? The one thing that is different with this, though, is water has a polarity to it, so it's almost like a magnet, has a positive end and a negative end, all right? And water molecules will arrange themselves so that those positive and negative ends line up. Okay, that's what makes water polar. It also is the reason that when you freeze water, water will kind of arrange itself a lot of space. Water. So that's why ice is less dense than liquid water. Okay, but a couple differences there between ionic and covalent bonds. Okay. Are there any questions at this point on anything? Yes, sir.
Can you just say what
A molecular compound? Sure. A molecular compound is just a molecule, which is a group of covalently bonded atoms. But it's a compound if it's made of more than one element. Okay, so for example, water is a molecular compound. Carbon dioxide, CO2, is a molecular compound. Methane, CH4, is a molecular compound. Okay. O2 and Cl2 would not be compounds because they're just that one thing, just oxygen, just chlorine. Okay, hence why we consider them their diatomics. But anything that's more than one type of element, those are your compounds. Okay. Other questions? All right, so let's do this. I'm going to keep rolling and go to section 2. So if we look, the first question they ask is, what's the difference between oxygen you breathe and the oxygen in the ozone layer? Oxygen we breathe is O2. That's a 2. So there's 2 oxygen atoms bonded together covalently. But ozone, which you've heard of the ozone layer, right, and the depletion of the ozone layer, this is supposed to show the hole in the ozone layer above Antarctica. O3 is ozone. So the difference is just 1 oxygen atom. Okay? But they both have very, very different properties. So what we want to look at is how are these two formed? How do these oxygens bond together with each other? And so that's what we're going to look at. And it starts with the octet rule. So the octet rule is what we talked about in ionic bonding, where each atom wants to have 8 valence electrons, right? That doesn't change. Okay, it's the same thing. Everything still wants 8 valence electrons, and they're going to do whatever's easiest. They're either going to gain or lose electrons to do that. Well, in this case, in covalent bonding, we already said that neither side wants to gain or give up electrons, right? So take, for example, chlorines. Chlorine has 7 valence electrons, yeah? And if you find one chlorine, you're probably going to find another, right? You're not just going to have one atom floating around in space. Now, if chlorine has 7 valence electrons, how many more does that chlorine want to gain? Just 1, right? Okay. So if each one of these wants to gain an electron, what you're not going to find is you're not going to find one of these chlorines donating an electron to the other. Because while that makes this one happy and satisfies its octet, the one over here now needs 2 valence electrons. It's in a worse off spot than it was before. So that's not going to happen. Instead, what happens is, let's name these for illustrative purposes. Chlorine number 1 gets their people together. Chlorine number 2 gets their people together. They talk, they have lunch, and they decide, well, let's share 1 electron each. I'll share 1 with you, you share 1 with me. And what that does, chlorine number 1 can now claim 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Chlorine number 2 can now claim 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And now both of them have satisfied their octet. They both have 8 valence electrons. Okay? An easier way to show this other than the electron dot diagrams is we can draw both chlorines. And we know that we have 1 shared pair of electrons. So covalent bonds are all about their electrons and pairing the electrons. These are shared pairs of electrons, right? 1 electron comes from the other. I want to show that there's only 1 shared pair of electrons between these two, so I'm just going to draw a straight line between them. So that one single straight line between these 2 chlorines shows that there is 1 shared pair of electrons holding those 2 together in a covalent bond. And we have a real fancy name for this type of bond with 1 shared pair of electrons. We call it a single bond. And then the chemical formula, there's 2 chlorines, so I'm just going to say Cl2. Okay? Good with that? Let me show you another example. Okay? Let's call oxygen. How many valence electrons does oxygen have? 6. Very good. So 6 here. If there are 6 valence electrons, how many more does oxygen want? 2. Again, let's name them thing 1 and thing 2. So if each oxygen wants 2 more valence electrons, again, their people confer, and they decide they're going to share 2 valence electrons. Each will share 2 electrons with the other. Now notice I circled each pair separately. Okay? I don't want you to circle all of them together because we want to see the individual shared pairs. Okay, so there's 2 shared pairs here. So now let's check. Oxygen number 1 has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Oxygen number 2 has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. both are happy. They both satisfied their octet. They have 8 valence electrons. Since there are 2 shared pairs of electrons, I'm going to draw 2 straight lines. And this also has a fancy name. You probably could guess it. That is a double bond. Again, 2 oxygens. That's your O2 molecule. What do you think? Single bond versus double bond. Which one do you think is stronger? Excellent. One more example to show you. If you start seeing a pattern, you may understand it. How many valence electrons does nitrogen have? 5. Now I'm going to put over here, and you can more. Well, on each double check. 1, 2, 3, 4, 5, 6, 7, 8 for this nitrogen. 1, 2, 3, 4, 5, 6, 7, 8 for this nitrogen. They're both good. 3 shared pairs for 3 lines there. What do you think we're going to call this one? Triple bond. Very good. And that is your nitrogen diatomic molecule. So we have single bonds, we have double bonds, we have triple bonds. Okay? If we look at one more example, let's look at a compound, such as CH4. We'll talk more about how the structure is known, but typically if you have a carbon atom, that's usually central, and then hydrogens or whatever else are around it. Carbon has 4 valence electrons. So this carbon wants 4 more, right? Now, big thing to understand. There are 4 hydrogens here, right? So let's just write one of them down. How many valence electrons for hydrogen? Just 1, right? Now, how many more does hydrogen want? Just 1 more. Because, if you recall, hydrogen has 1 valence electron. Here's a nucleus. There's that. In order to fill its outer energy level, which for hydrogen is the first energy level, it only needs 1 more electron because that first energy level can only hold 2 electrons total. So hydrogen is one of our exceptions to that octet rule because it only wants 1 more electron. So, as you're saying, this hydrogen will share electron with carbon, carbon will share with hydrogen, and by doing so, this hydrogen has its 2 valence electrons, so it's good. Now we said there's 4 hydrogens, so again, you're going to see this 3 more times. Each hydrogen now has 2 electrons to its name. Each one is good. What about carbon in the middle? 1, 2, 3, 4, 5, 6, 7, 8. The middle is good. And so then we have carbon with a single bond to each one of those hydrogens. You had a question?
I don't know if you can explain it any different, but I don't really understand the hydrogen only 2.
So everything needs 8, right? That's kind of the standard issue. Let's say we go to a stadium. Here's the section we're sitting in. Okay? So here's a row, here's a row, here's a row, so on and so forth. Each one of those rows has 8 seats. Okay? And boom, boom, boom. The first row, though, only has 2 seats. So the whole goal is to have your last row of electrons to be completely full, right? Because then you're not really needing anything, if that makes sense. So if you have an outer energy level that has less than its maximum capacity, an atom is going to do what it can to either fill that row up or to kick the electrons in that row out, right? If I have one electron here, let's say this is full, this whole row is full. If I only have one person here, I'm either going to try to find 7 more people to fill it in, or I'm going to make this one person move out, making this my new outer energy level. Okay? Well, with hydrogen, there's only one valence electron, and it's found in that first energy level. And the first energy level only holds 2 electrons. It's only that big, right? Just like the first row here only has 2 seats. So if one of them's already full, hydrogen only wants to find one more electron. Because if hydrogen, let's say hydrogen found 7 more electrons, okay, just to appease the octet rule. So it has its 1. There's 1 more, 2 more, 3 more, 4 more, 5 more, 6 more, 7 more. That means now there's 2 empty spots in its second energy level. And it still needs to find 2 more to fill that, which at that point is way too big for it to be hydrogen. Does that make sense? So hydrogen is kind of our exception to the 8 rule, but it still holds true in filling that outer energy level. But hydrogen only owns electrons. Its electron configuration now becomes like helium, which is a noble gas. So it's still all about trying to be like a noble gas. Okay, that's a good question though. But that is a very important thing to understand is hydrogen is that one exception, right? It only wants 2 valence electrons when everything else wants 8.
Is that the only exception?
Other than helium, but helium won't make a reaction, right? Helium won't bond with anything else. So for our intent purposes, yes. Okay, good question. Any others? Okay. There's not a whole lot more out of section 2 that I want to cover right now. So the official notes go through single bond we talked about. The only other thing I'll show you is here you can see hydrogens. You can see the dots stacked up on top of each other as opposed to how I drew them side by side. It's no different. It's the same thing. Just know that in this case, 1 electron comes from this hydrogen, 1 comes from this one. HHS. Man, it's a tough crowd. Single bond. It talks about unshared pair of electrons. We'll get to that in a little bit. We'll get to that next class. Okay. But unshared pairs of electrons are extremely important, especially when we start talking about the structure of the molecules and how they're shaped. Double bonds, triple bonds, they start talking about. We will also next time start talking about, I'll just briefly mention coordinate covalent bonds, polyatomics, and that'll be about it. We're not really going to get into exceptions. We'll talk a little bit about bond dissociation energy and resonance, and that's about it. Okay, so this is a good starting point for us. Questions right now? Okay. So just real quick to show you our agenda. We went over 8.1 and most of 8.2. Okay. On Google Classroom, you'll see a worksheet for 8.1. See if I can show it to you. Okay. 8.1 worksheet, covalent bonding. So it's along with notes here as well. Okay. And then discuss covalent bonding. There are 2 videos. Kind of talks about all the things I just showed you. If you want to know, you feel more than welcome to. It'll definitely help you. And then after that, complete the covalent bonding practice worksheet that is on here. You're going to notice it basically the same style worksheet as the one we did for ionic bonding. It gives you the elements, asks you for the number of protons, number of electrons, valence electrons, and then number of electrons to fill its outer energy level. Okay? And then it gives you two atoms, so for example, hydrogen, hydrogen. We know that each one has one valence electron. We know that each one wants to gain one more. So they're both going to share an electron. That's going to form a single bond between hydrogens, and then the formula is just H2. Okay? So that's what I want to see written out for each one of these. If you scroll down, the answer key is attached to it just like it was for the ionic bonds. That way you can check your work. And if you have any questions, you can let me know.